So today we're looking at doing a little modeling and writing absolute value functions when we're given the graph. So we have our standard form for when we do our graphing with our different transformations, our horizontal, our vertical translations, and then our dilations. So based on this, when we have values other than 1 for both a and b, we can rewrite that function so that the value of at least one of a or b is 1. So when a and b are both positive, we can write our equations like this. The key here, usually when we're working through these, we want b to be 1 just because that b is part of the horizontal stretching and compressing, and that's what we're not dealing with. So usually we're going to just say we're going to let b be 1 and solve for a in our equations. Again, it's easy to find the h and the k values just because that's from our vertex. So the dilation key is mostly what we're solving for today. So we have an example here. We're given a graph. And again, we're going to let b be 1 since that represents that horizontal dilation that we're not really worried about. So the vertex of our graph we can see here is at 1, 6. So that means that horizontally our h is 1 because we're moving to the right. K is 6 because we're moving up. So again, we said the value of b is 1. So if we plug those values from the vertex into our standard transformation equation, so we'll get g of x is equal to a absolute value of x minus 1. Again, that means we're moving to the right one, and then plus 6. So we use the vertex to create the standard graph, and then to find that a value, that vertical dilation, what we're doing there, we just pick another point that exists on our graph. So in this case, they give us the coordinate 0, 3. So we're going to plug those values into our equation and then solve for a. So again, our equation says a times the absolute value, x minus 1 plus 6. So we plug in our values. So g of x, again, that's the output, that's the y value. So that would be 3 is equal to a times the absolute value of 0. 0 is the x value of our point. So 0 minus 1 plus 6. So we still have this 3 here. 0 minus 1 is negative 1. So when we solve from here, absolute value of negative 1 is just 1. This will be 1a plus 6. So to solve for a, we'll subtract the 6 to get a is negative 3. And then we can rewrite our equation. So it'll be negative 3 absolute value, x minus 1, close our absolute value, plus 6. So we can also use this for modeling. So for example, here we've got light travels in a straight line and can be modeled by a linear function. When light is reflected off a mirror, it travels in a straight line in a different direction. So from physics, the angle at which the light ray comes in is equal to the angle at which it is reflected away. The angle of incidence is equal to the angle of reflection. So we can use an absolute value function to model this situation. So we want to solve this problem by modeling with an absolute value function. So at a Science Museum exhibit, a beam of light originates at a point 10 feet off the floor. That's a good thing to recognize, 10 feet off the floor. It's reflected off a mirror on the floor that is 15 feet from the wall the light originates from. So we're trying to determine how high off the floor on the opposite wall does the light hit if the other wall is 8.5 feet from the mirror. So check the next video and we will continue with this example.